Hello everybody, this is Dr. Dave with Physics 150. There were a number of people in class this week having a difficult time with circular motion and setting up their free body diagrams still, and once they'd set those free body diagrams up, kind of knowing what to do with them. So I thought I would go through a couple of quick examples that might help you with your homework this week. They're may not appear directly applicable, but I do promise that they will help you. So let's imagine we have a box sitting at an incline as shown at some angle theta. In the first case, we want to consider what if the acceleration of the object is equal to 0. Well, if you draw your free body diagram in the standard way, you get your weight force down, your normal up, and your friction that way. However, those magnitudes are not drawn arbitrarily. We know that this part of the normal force has to equal that part of the weight, and that this part of the friction has to equal that part of the weight. Hopefully that's review for everybody. We then have an angle of this incline which has to get added to this diagram. And I'm going to admit here that putting that angle in the right place is a little bit tricky. Some people find it easier to draw the triangle on this side and then they're able to see that the angle theta goes here. That might work for you. Another thing you can do is to ask yourself the following question. What will the weight vector do? That is the vector here. What will that do as this angle goes to theta? Will that weight vector become more like your y direction or more like your x direction? And that can then help you if you know your trig values, of course. So the angle is here, and we then just do standard trigonometry. We take cosine of our angle and we do sine of our angle, and we find these results for the following coordinate system of x and y. This is hopefully just straight up review from the last 2 weeks. Then we go and we sum our forces in the y direction, and this is where people were asking for help. So if I sum the forces in the y direction, what I'm asking is what forces are acting in this direction, which is what I've chosen to be my y. Well, the normal force is acting vertically, or not vertically, but along the direction of y, so I have it here as positive. And then the weight force isn't in x or y, it's again got its components, but the weight component in the y direction is negative in the opposite direction. So I have now created my sum of my forces. Newton's second law tells me that once I have summed my forces, I may then set them equal to ma. Ma is not a force. It is simply what the sum of forces are equal to. Given that I have said the acceleration of this object is 0, that sum of the forces is equal to ay, which is also 0, allowing us to solve for our normal force. And so we see here in this circumstance the normal is equal to mg cos theta. Remember that cosine and sine are functions that are bounded between -1 and 1, so therefore this is saying the normal force at most could ever equal the weight. And in this particular circumstance, that's correct. The normal force can exceed the weight, however, if the motion requires it, but that's going to be more of a circular motion type issue that we'll see a little bit later going on. And I say here to check the scaling. What do I mean by that? Well, if this angle theta were to go to 0, that means this incline would fall down, right? It would just be flat. So the question is, how much of that weight force would you expect to be in the x direction? Well, if the incline goes flat, the x direction is this way, we would hope none of our weight force would be in that direction. So here what do we see? The normal is mg cos theta. Sorry, I said that wrong. Y direction. This is our y direction. As theta goes to 0, that y direction becomes vertical. And so as theta is plugged in here for 0, cosine of 0 is 1. That says the normal equals the weight, and that's the sort of thing we expect. We then go on to check the x equations. We say, okay, weight is not, again, in the x or y direction. It has a component in the x and a component in the y. So we have weight x. In this case, we said down incline is positive. So weight is positive. And friction is going up the incline, which we then say is negative. So we've now done the sum of the forces. We've plugged in Newton's second law, and we find that friction is that. Hopefully, no one has any confusion up to that point. However, if you do, please see us right away in office hours so we can give you a hand. What, however, do we do if we know the acceleration is not 0? So let's consider the second case, if the acceleration is up the incline. So we need to now find, what is the acceleration if we're given some force of friction. So let's remind ourselves, why we had no acceleration in our previous drawing. That is, we had our normal, or our weight, our normal, and our friction. When we added these three vectors together, we ended up back at the origin where we started. So the sum of those three vectors was equal to 0. If, however, we now make friction a little bit bigger, that means our weight is there, our normal is there, and our friction ends here. Well, the net force is now from where you start to where you stop the vector addition. So our F net is now this little purple vector right there. So that would give us a net force up the incline, which would mean the acceleration is then up the incline. So if we go ahead and we sum our forces, keeping in mind our original coordinate system that down the incline was positive, which is going to create a little bit of an awkward moment, but we're going to see how to resolve it here. We then get weight is positive because the weight acts is down the incline. The friction is going to be negative because it's up the incline. And that's going to equal max. So, what do I mean things are going to get a little bit awkward? We know the acceleration is up the incline. But if you were to look at your answer here, that's not clear that the acceleration is going to be negative or up the incline. This is why we recommend that you choose your coordinate system to align with the direction of acceleration. So in this case, we really should, just for ease, it's not wrong to do it the other way, just for ease, make up the incline our positive direction. We didn't, however. So what that means is we continue forth with what we're doing, and we know at the end of the day that this result should be negative. So if you get a result like that, where you know the acceleration is not in the same direction as your coordinate system, you should make that clear to us. You should make it clear that you have made a choice that's going to result in a result that is negative, even though it's not obvious. What does it mean that's negative? Well, it means that this friction divided by mass has to be bigger than g sine theta. The moral of the story is, at the end of the day, choose your coordinate system to be in the same direction as your acceleration to make your life simpler. As another note, if you ever solve for a force and get a negative, meaning if you didn't know what way friction was and you had to guess, if you ever solve for a force and you get a negative, your force should be in the opposite direction. And so what happens if your force should be in the opposite direction, but your force can't be in the opposite direction? What do I mean by that? Could this normal be directed downward? Could the interaction of this surface cause this block to be pulled down? I hope you would agree the answer is no. Maybe if there was Velcro or something like that going on, but in general, no. The normal or that interaction from that surface is going to be this way, not that way. So if you get an answer that your normal should be negative, you've got two choices, or two options. One, the circumstance is unphysical, meaning for this thing to occur, your normal would have to be the wrong direction. Therefore, that's not possible. The other possibility is that you made a sign error. Go back and check. So if we ever get a negative force when we solve, that means your force should have been the opposite direction. If it's not possible for that force to be in the opposite direction, then you know you've entered the realm of not being possible, not physical. Right? What's another not physical thing? Let's imagine you get tension to be a push. You can't really push with a string. You can try it. It's funny. Maybe make a video. I'd like to watch it. It doesn't work. All right. So let's look at something a little bit more challenging, something a little bit more topically equivalent or on par with what we're doing this week. So now what do we have? Here I want to draw a case of circular motion. This is going to be a vertical thing. So imagine you have your keys on a chain and you're twirling them around in a vertical circle, meaning they're slowing down as they go up and they're speeding back up as they go down. And so now I'm going to say, all right, let's draw a free body diagram for this circumstance. And I'm going to place my angle theta here. So now this thing is going up and around. It goes, slows down, speeds up, slows down, speeds up, right as it moves around that circle. So what are the forces? Well, at this arbitrary point defined by theta as given, I've drawn the free body diagram as such. I drew the weight like normal, and then I drew the tangent along the direction of the string. Why? Well, because you can't push with a string, so the only way you can create tension is along its length. We then choose a coordinate system. In this case, we're going to choose it to be radial inward, and you really never want to change that. You really want radial to be inward to your curve. And I'm going to choose tangent to be along the direction of motion, which may not be the most convenient for this moment, but because this thing is slowing down and speeding up as it goes, the direction of my acceleration is constantly changing, so there isn't a convenient way to just pick it to always be plus. So I'm going to choose it to be in the direction of motion. So now I've drawn my forces. Well, with this coordinate system, my tension is going to be in the radial direction, but my weight is not only radial or only tangential, so I have to break it down. So I come over and I draw my weight vector, and then I say, okay, I'm going to have a tangent component and a radial component. You might wonder, how the heck did I go from that angle here to this angle here? There's a number of different ways to do it. You draw different triangles and you try to figure out what's going on. You can draw a triangle here and then try to break that up. It's up to you. The way I find the most easy is I check what's called the scaling behavior. What the heck does that mean? Well, if this theta goes to 0, that means I'm right here, right? What do I expect from my weight? Is any of my weight going to be radial? No, right? It's all going to be tangential. So then I write down the equation such that that's true, because I know it's going to be either that angle or that angle. So which one is it? It's the one that gives me all the weight in the tangential direction and none of the weight in the radial direction. Great. So that's how you break down the radial and tangential components. Now it's time to sum the forces. So we say sum the forces in the radial, and this really is just look at the diagram and read it. Which forces point radially? Tension, check. Weight, not all of it, just the radial rate. And there we go. We plug that in. And that radial sum per Newton's second law will be equal to ma radial. We have a new thing in this chapter, a new acceleration constraint, and that is circular motion. Circular motion requires that your radial acceleration be v squared over the radius of the curve. In this particular problem, the radius of that thing is L, so I'm going to write it as t plus mg sine theta equals mv squared over L, which allows me to solve for the tension, presuming that I knew my tangential speed or whatever, but allows me to solve for the tension. So I can now know my tension as a function of v squared. This isn't exactly the problem we've asked you to do in the homework, but it's pretty close, so you should be able to make some progress there. So now the question is, what is the sum of the forces in the tangential direction? Well, positive tangent is this way. However, the weight is in the negative direction, so I'm going to put that explicitly in there now. So then I'm going to get, I just noticed a math error here. Now I'm going to get minus w weight tangent is minus mg cos theta equals mat. Solving for that, I then see the tangential acceleration is negative g cos theta. We want to make sure that's right. Let's go back to our theta equals 0 condition. That is right here. Is it okay that the acceleration is downward, right? That's negative tangent at minus g. And the answer is yeah, it is. We said going upwards at this point in time is positive, so that's a correct statement. If you don't know your cosine and your sine at 0, 90, 180, 270, etc., your life is harder in physics for no good reason. It's 4 values. You can do it. Many of them are 0. You can do it. Learn it for the next 5 weeks, maybe the next 15. It will help. All right. So if theta equals 0 degrees, that says AT is minus G. Is that good? Yeah, that's good. If theta is 90 degrees, that says the tangential acceleration is 0. Does that make sense? If I'm right here, is there no acceleration in that direction? That's right, there isn't. Both your tension and your weight are down. If theta is 180 degrees, that says AT is plus G. Well, why the heck does it change sign? If this is 180 degrees, right, that's 180 degrees, does it make sense that the acceleration is now in the positive tangent direction? Yeah, because at this point here, G is down, the tangential direction is down, so it is now in the positive direction. Good. So here's a physics question. Everything up to this is just math. This is physics. Is there a minimum speed? Think about that. This object is going to slow down as it goes up, and then speed up as it's falling, and then slowing down as it's going up, right? So it's speeding up this half, and it's slowing down this half. Can I reach the top with 0 speed? I suspect some of you imagine the answer is yes. Sure, I could reach the top at a minimum speed. But can I? I suggest that you do this. Grab something, put it on the end of a string. Probably not your phone on your charger, but something, your keychain. You got to have a piece of string or something, right? Pick it up, swing it around, go slower and slower. Pause the video. I guess I don't need to stop talking if you've actually paused it, but try this. You'll see that the answer is yes, there is a minimum speed. At some point, it won't finish the circle. It will just fall. So how do we envision that? Well, remember what we said. If a force becomes negative, it has to be in the opposite direction. So when I look at this equation right here, is it possible for tension to become negative? And the answer is sure. If this piece here is bigger than that piece, it'll be negative. But we know you can't have negative tension. The math does what you tell it to do. So in this case, the math says, sure, go negative. I don't care. It doesn't know what tension means. But we know, we're smarter than the math. We know tension can't be negative. So we know that whatever these terms are added together, they have to be greater than or equal to 0. So let's explore that. All right. So what is the tension at different places? At 0 degrees, we plug in 0 into our tension equation. Sine of 0 is 0. That's our tension. At 90 degrees, straight up and down, here's our tension. At 180 degrees, there's our tension. At 270, there's our tension. This is a whole lot of letters. And when you look at this, it may not mean much to you. And that's fine. Over time, it should mean more. So why did I write this like extra theta stuff here? That's a whole lot of extra letters to look at. Well, what did we say? We said that the object slows down as it climbs and speeds up as it comes down. So I have to denote that Vt is not the same at every point. The tangential speed is different. So how did I denote that? I denoted it by the angle that it occurs. So that's the tension, right? This is T equals, T equals, T equals, etc., etc. Does that mean there's a minimum? Let's think about that for a minute. Can the tension ever become 0 or negative, right? Because negative tension is when we know that can't happen. Can this be negative? Think about it. Mass, length, square of a velocity, there's nothing in there that can ever be negative. So there's no problem here. What about here? Same idea. Mass, length, Vt squared, nothing's ever negative. What about this here? Nothing's ever negative. The only time we get that negative is right here. So this is the only time that we need to consider as our minimum tension. All right. So let's make a plot of what our tension looks like at the top, right? Because that's what 90 is, at the top for as a function of velocity. So what do we get? We've got tension equals this quantity here. For simplicity, I'm just going to say v squared now. So it's mv squared by L minus mg. If I make a plot of tension versus v squared, that turns this into a y equals m x plus b circumstance. So my intercept here is minus mg. There's my intercept. That says if I'm not moving, my tension has to be minus mg for that motion to occur. Is that possible? No, I cannot push with a rope, right? That says the tension has to be pushing upward for that to occur. So I can't have 0 speed. Well, I can't just have any speed squared. I have to get all the way, what? To this point. And once you reach this point, you're now at a place in which you could have tension 0 or greater, and motion could occur. So what is that? That's your minimum speed. So what is minimum speed algebraically? So minimum speed occurs when t is 0. We can't go slower and maintain circular motion. because at the top, tension is down, mg is down. So at 0 tension, all I have is mg. So the sum of radial forces is T plus mg. T is going to be 0, just mg. The sum of the forces equals ma. That A is v squared by r. We can solve it now and see that Vt is square root of GL. That's your minimum speed. That is the speed that you cannot go slower than if you want to complete the circle. I hope this has been helpful, or at least not confused you more. Thank you for your time. Please continue to reach out to us in office hours and get help.